Hello everyone and welcome to Lecture 11 of our Probability Theory course. Today we're going to explore one of the most fascinating and important topics in all of probability and statistics, the law of large numbers and limit theorems. These theorems explain why randomness becomes predictable with enough data, and they form the foundation of modern statistical inference. Here's our plan for today's lecture. We'll begin by understanding why we need limit theorems in the first place. Then we'll explore the law of large numbers and its intuition. We'll introduce Chebyshev's inequality, which is a crucial tool for proving limit theorems. We'll then cover Chebyshev's theorem, also known as the weak law of large numbers, and Bernoulli's theorem as a special case. After that, we'll move to the most important theorem in statistics, the central limit theorem, and its special case, the De Moivre-Laplace theorem for the binomial distribution. We'll discuss applications and finish with a summary of key takeaways. So why do we need limit theorems? Let's start with a key question. What happens when we repeat an experiment many times? Consider tossing a coin. If you toss it 10 times, the number of heads might be 3, 5, or even 8. The result is highly variable and unpredictable. But if you toss the coin 1,000 times, the number of heads will be very close to 500. Why does this happen? The reason is that the frequency of an event stabilizes around its true probability as we perform more and more trials. This is a fundamental insight that underlies all of probability theory. Limit theorems provide rigorous mathematical answers to important questions. Does the average of many observations stabilize? What is the distribution of the sum of many random variables? And how accurate are our estimates when we use samples to make inferences about populations? These theorems are essential for understanding how probability connects to the real world. There are two most important theorems in probability and statistics. First, the law of large numbers, which tells us that averages stabilize as we collect more data. Second, the central limit theorem, which tells us that sums of many random variables become normally distributed regardless of the original distribution. These two theorems together justify why statistical methods work and why we can make reliable predictions from data. Let's develop some intuition for the law of large numbers. The simple idea is this: as the number of trials increases, the sample average converges to the expected value. Consider the coin toss experiment again. With 10 tosses, the proportion of heads might be 0.3 or 0.7. It's unstable and varies a lot. With 100 tosses, it's much closer to 0.5. With 1,000 tosses, it's very close to 0.5. And with 10,000 tosses, it's almost exactly 0.5. In general, the average of x1 plus x2 plus xn divided by n converges to the expected value, which we denote by mu. The key insight is that randomness averages out over many trials. The more data we collect, the more accurate our estimates become. This is why we can trust averages from large samples. Before we can prove the law of large numbers rigorously, we need an important mathematical tool called Chebyshev's inequality. It's named after the Russian mathematician Pafnuty Chebyshev, who lived from 1821 to 1894. This inequality states that for any random variable x with finite mean mu and variance sigma squared, the probability that x deviates from its mean by more than epsilon is at most sigma squared divided by epsilon squared. Equivalently, the probability that x deviates by less than epsilon is at least 1 minus sigma squared over epsilon squared. This is a remarkable result because it works for any distribution, regardless of its shape, as long as we know the variance. It shows that large deviations from the mean are unlikely, and it allows us to bound probabilities using only the mean and variance. We don't need to know the entire distribution to make probabilistic statements about deviations from the mean. Let's work through a concrete example to see how Chebyshev's inequality works in practice. Suppose we have a random variable x with mean 10 and variance 4. We want to find the probability that x deviates from the mean by more than 3. Using Chebyshev's inequality, we get that the probability of x minus 10 being greater than or equal to 3 is less than or equal to 4 divided by 9, which is approximately 0.444. Equivalently, the probability that x is within 3 units of the mean is at least 1 minus 4 over 9, which is 5 over 9, approximately 0.556 or 55.6%. This means that at least 55.6% of the values fall within 3 units of the mean. It's important to note that this is a weak bound as the actual probability is usually much higher. Chebyshev's inequality gives us a conservative guarantee that works for any distribution. Now we can use Chebyshev's inequality to prove the weak law of large numbers, also known as Chebyshev's theorem. The statement is this: let x1, x2, up to xn be independent random variables with the same mean mu and finite variance sigma squared. Then the probability that the sample average differs from the true mean by more than epsilon goes to 0 as n goes to infinity. In other words, the sample average converges in probability to the true mean. The proof uses Chebyshev's inequality applied to the sample average. The variance of the sample average is sigma squared divided by n, so the bound becomes sigma squared divided by n times epsilon squared, which approaches 0 as n grows. This is a powerful result. It tells us that with enough data, we can estimate the true mean with arbitrary accuracy. The probability of a large error becomes vanishingly small as the sample size increases. A special case of the law of large numbers is Bernoulli's theorem. This applies when we have independent Bernoulli trials. Each trial is a success or failure with probability p. Let m be the number of successes in n trials. Bernoulli's theorem states that the relative frequency m over n converges to the probability p as n goes to infinity. In words, the relative frequency of successes converges to the probability of success. This theorem provides the rigorous justification that probability equals long-run relative frequency. It means that if we toss a coin enough times, the proportion of heads will be very close to 0.5. This is the foundation of the frequentist interpretation of probability, which is essential for understanding how probability connects to real-world observations and experiments. Now we come to the most important theorem in all of probability and statistics, the central limit theorem, often abbreviated as CLT. The statement is this: let x1, x2, up to xn be independent random variables with the same distribution mean mu and finite variance sigma squared. Then the standardized sum converges to a standard normal distribution as n goes to infinity. In words, the sum of a large number of independent random variables is approximately normally distributed, regardless of the original distribution. This is an astonishing result. It explains why the normal distribution, also called the Gaussian distribution, appears everywhere in nature and statistics. Whether we're adding measurements, errors, or any other quantities, the result tends to be normal. This theorem is the reason why we use normal-based methods for hypothesis testing, confidence intervals, and many other statistical procedures. For practical purposes, the central limit theorem tells us that for large n, typically n greater than or equal to 30, the sample average is approximately normal with mean mu and variance sigma squared over n. Equivalently, the sum of the variables is approximately normal with mean n times mu and variance n times sigma squared. What does this mean in practice? First, averages are approximately normal, regardless of the original distribution. Second, sums are approximately normal. Third, this works for any original distribution. It doesn't matter if the data comes from a uniform, exponential, or any other distribution. Fourth, only two things matter: the mean mu and the variance sigma squared. This theorem was first proved by Laplace and later generalized by Lyapunov. It's the foundation of much of modern statistics. A special case of the central limit theorem is the De Moivre-Laplace theorem, which applies specifically to the binomial distribution. It states that if x has a binomial distribution with parameters n and p, then for large n, the standardized binomial variable is approximately standard normal. In other words, the binomial distribution can be approximated by the normal distribution for large n. The rule of thumb is to use this approximation when n is at least 30, and both n times p and n times q are at least 5. This approximation is very useful because calculating binomial probabilities for large n can be computationally intensive. The normal approximation provides a much simpler way to compute probabilities. This was the first central limit theorem ever discovered by Abraham de Moivre in 1733, and it was later refined by Pierre-Simon Laplace. Let me now provide a comprehensive summary of everything we've learned in today's lecture. We covered 6 key concepts that form the foundation of probability theory and statistical inference. First, the law of large numbers. This is a fundamental theorem that tells us something very intuitive, yet mathematically profound. As the sample size grows larger and larger, the sample average converges to the true expected value of the distribution. In simpler terms, if we repeat an experiment many times, the average of our observations will get closer and closer to the theoretical mean. Similarly, the relative frequency of successes, that is, the proportion of times an event occurs, converges to the true probability of that event. This is why we can say that if we toss a fair coin 10,000 times, the proportion of heads will be almost exactly 0.5. The law of large numbers gives us the theoretical justification for the frequentist interpretation of probability. That probability is the long-run relative frequency of an event. Second, Chebyshev's inequality. This is a powerful mathematical tool that allows us to bound the probability that a random variable deviates from its mean by more than a certain amount. The inequality states that the probability of such a deviation is at most the variance divided by the square of the deviation threshold. What makes this inequality so remarkable is that it works for any distribution regardless of its shape, as long as we know the mean and variance. We don't need to know the full distribution to make statements about how likely large deviations are. This is incredibly useful in practice because in many real-world situations, we may not know the exact distribution, but we can often estimate the mean and variance. Third, Chebyshev's theorem, also known as the weak law of large numbers. This theorem uses Chebyshev's inequality to provide a rigorous proof of the law of large numbers. It states that as the number of observations increases, the probability that the sample average differs from the true mean by more than any positive amount epsilon goes to 0. In other words, the sample average converges in probability to the true mean. This is a precise mathematical statement that quantifies how the uncertainty in our estimates decreases as we collect more data. Fourth, Bernoulli's theorem. This is a special case of the law of large numbers that applies specifically to Bernoulli trials, experiments with only two possible outcomes, success or failure. Bernoulli's theorem states that the relative frequency of successes converges to the probability of success as the number of trials increases. This theorem provides the rigorous justification that probability equals long-run relative frequency, which is the foundation of the frequentist approach to probability. It's what allows us to say that if we flip a coin many times, the proportion of heads will approach 0.5. Fifth, the central limit theorem. This is arguably the most important theorem in all of probability and statistics. The theorem states that the sum of a large number of independent random variables is approximately normally distributed, regardless of the original distribution of those variables. This is an absolutely astonishing result. It explains why the normal distribution, also called the Gaussian distribution or the bell curve, appears everywhere in nature, in heights of people, in measurement errors, in stock returns, and countless other phenomena. The central limit theorem is the reason why we can use normal-based statistical methods for hypothesis testing and confidence intervals, even when we don't know the underlying distribution of our data. Sixth, the De Moivre-Laplace theorem. This is a special case of the central limit theorem that applies specifically to the binomial distribution. It states that for large n, the binomial distribution can be approximated by the normal distribution. This was actually the first central limit theorem ever discovered by Abraham de Moivre in 1733 and later refined by Pierre-Simon Laplace. The practical significance is enormous. Calculating binomial probabilities for large n can be computationally intensive, but the normal approximation provides a much simpler and faster way to compute these probabilities. The rule of thumb is to use this approximation when n is at least 30 and both n times p and n times q are at least 5. The key takeaway from today's lecture is this: with enough data, randomness disappears and reliable patterns emerge. While individual observations may be unpredictable, the averages and sums of many observations become highly predictable. This is the fundamental insight that makes statistics possible. These theorems justify why we can trust conclusions based on large samples and why we can use sample data to make inferences about populations. The law of large numbers assures us that our estimates will converge to the true values, and the central limit theorem assures us that we can use the normal distribution to quantify the uncertainty in our estimates. Together, these theorems form the mathematical foundation of modern statistical inference. They are the reason why we can conduct opinion polls, perform clinical trials, monitor quality control in manufacturing, and make countless other decisions based on data. Without these theorems, statistics as we know it would not exist. So as you continue your studies in probability and statistics, remember these fundamental results. They are the backbone of the entire field. That concludes our lecture. Thank you for your attention.